So I'm from Borealis, so I'm not going to talk about all the cool research we do because you heard about it during the community crawl. Thank you for coming out to our lab. I will mention, though, that we have fellowships, in case you missed this announcement. So if you are a Canadian graduate student doing something in AI or machine learning, you're eligible. So it's a nice $10,000 fellowship. You can apply, it doesn't take too long. Go for it. We need more good RL people winning this fellowship, I think. So I wanted to talk to you today about human-in-the-loop stuff. So autonomy is awesome. We've been learning about these agents that can do all this cool stuff. But the question is, a lot of the times there is a human. There's someone sitting there. What can we do with them? How can they be useful? So I want you to take 1 minute, meet the person next to you, and brainstorm some ideas. Go. Okay. Thank you, everyone. Thanks for getting into this. Good minute. Okay, now you have to stop talking. Thank you. Okay, who's got an idea they can throw out? How can we leverage a human? Yeah. Awesome. So so the human could, say we want to learn a game, then the human could start playing that game and we could look at examples. What else could we do? So can you give an example? Cool. So the agent is playing a game, and you could do a few things. You could say, stop, that was stupid. You could say, good job. You could say, stop, you should have gone up there. Those are all valid things to do. Other ideas? Yeah? The agent could ask for advice when it's uncertain. Okay, so a couple ideas there. First is, the agent could proactively say, help, I'm confused. Another point is when I'm uncertain. So if the agent has some ideas about when it's confused, when it's not sure, or maybe it realizes there's a critical decision coming up. Maybe it realizes, oh, if I don't do exactly the right thing, I'm going to lose the game. So maybe there's something there. And there's also the question of what we mean by advice. So the easiest thing would be, oh, agent, go up. But you could also do things like natural language advice. Agent, stay away from the edge of the cliff. Agent, always jump on top of the enemies, don't run into them. Stuff like that. Good. Any other ideas? Yeah? Okay, so can you give an example? Okay. Yep. So if the human knows something about the particular task, that could help the agent somehow speed up learning. Another thing that humans are really good at is common sense reasoning. So things like, oh, you don't want to fall off the cliff in this game. That's something that we kind of intuit very quickly, but agents may take a while to learn. Okay, any last ideas? Yeah, in the back.
The human can actually provide rewards, especially when the reward is particularly specified.
Yes. So we'll be talking about this in a little bit, where the human can actually provide the rewards to the agent. So the reason I wanted you to start thinking about this is really an open area. There's lots of ways. My hypothesis is there are lots of ways that we can leverage humans, and we're currently only doing a few of these. So it's great that, that DeepMind can make agents that can learn Go from scratch. That's really cool. And it takes, days and days or years of training. But in cases where there is a human, let's figure out how to leverage them. So what I'm going to talk about today is mostly looking at giving examples. So learning from demonstration, having someone perform the task, and then speed up learning from that. And then, depending on how much time we have, we'll go into providing rewards. So how we can train an agent like we train a dog, for instance. So I have probably an hour and a half worth of slides. I purposely have too much to go through. So I'm not expecting to get through everything. The slides will be available. We'll put it in that shared folder. But I wanted to make this as interactive as possible. So you all have been doing a pretty good job of asking questions and interrupting. So please continue to do that, because this will be much more fun for me if we make this interactive. Okay, so now we've got some idea of where we want to go today. Start with a little bit of history. So we can think of, in the 80s, programming by demonstration. So this is the idea of, I want the agent to just do what I want it to do. So there's no reward that it's trying to maximize. It's just trying to mimic. So there's also, with this programming by demonstration, there is no generalization, very sensitive to noise. But it was a cool start. Then we started doing generalization over multiple demonstrations. So things like close to or above, still very hand-coded. But then, finally, we get into actually using machine learning. So now we can analyze the demonstrations and try to generalize. This is always the interesting thing. If someone gives you a demonstration, then if you follow that demonstration perfectly, you're okay. Where you get into trouble is if you get just a little bit off. So think of a robot picking up a bowl. If the bowl is in exactly the same place every time, you can do a reasonably good job. But if the bowl moves a little bit, or you get a little bit of noise in your sensors, or a little bit of noise in your actuators, then you have to generalize. So we can think of two general frameworks when we're thinking about learning from a demonstration. Oh, I should mention, I'm going to be focusing on learning from demonstration, where we're assuming that we know exactly what the teacher was doing. There's also the idea of imitation learning. So if you're watching someone, and someone is trying to put himself in a pose and have the robot copy that. So that's more imitation learning. So we're going to focus on learning from demonstration. And there's really two kinds of classes of learning from demonstration. The first is behavior cloning. So behavior cloning is, I'm going to look at what the person is doing, and I'm just going to try to copy that. I'm going to try to copy their actions. The other one is inverse reinforcement learning. So let me go into a little more detail on these. So with inverse reinforcement learning, what I'm doing is saying, I've got a teacher, and that teacher is acting optimally for some reward function. I don't know what the reward function is, but let me assume the teacher's optimal and figure out what reward they would be maximizing. So this normally happens in an MDP/R. So this is the setting where I know my transition probabilities, I know my state space, I just don't have the reward function. So a common setting for this is a simple car driving domain. So you're driving the car and you're watching someone and you're like seeing how aggressive they are. Do they tailgate? Or do they stay further away from the cars in front of them? Do they stay on the road, or do they enjoy driving in the grass? So you watch a person do this, and then you try to figure out what reward they're maximizing. Yeah?
What's the difference between inverse RL and the imitation learning? Because both you are using methods which are you are trying to.
Yeah, so inverse or IRL, inverse reinforcement learning, is basically a type of learning from demonstration. The distinction I was making with the imitation learning was saying that we don't know exactly what the states and actions of the demonstrator are, so we have to look at them and estimate them. This comes into, there's been a bunch of recent work on learning from YouTube videos. So if I watch someone playing a game on YouTube, then there might be some uncertainty in the state because just because of camera artifacts, but also I don't know what actions they're taking necessarily. I just see the transitions. So with this inverse reinforcement learning, commonly we know everything. We've got a full model of the environment. So like we were talking about yesterday with Martha, if you were able to just be given one of these models and you could try to learn the reward function. There's also one method for model-free inverse reinforcement learning. So that's an example where you actually go and don't have a model of the world, but you're still trying to learn the reward that the person is maximizing. So one of the problems is IRL, inverse reinforcement learning, is underspecified. So for a given set of demonstrations, there's many, possibly an infinite number of rewards that that person could have been maximizing. So you've got to deal with that somehow. So IRL is one way to do this learning from demonstration. Another way to do it is what I mentioned before, behavior cloning. So this, in some sense, is a simpler method. It's saying, I'm going to look at the states and actions that the person took, and I'm going to try to derive a policy from that. So remember, a policy is just a mapping from states to actions. So you could look at what the person is doing and come up with a classifier. So to say, for a given state, what action do I think the person would take? So I'm going to be talking about this behavior cloning first. And the first method, so if you had a human and you wanted to try to mimic them, the algorithm I'd recommend you start with is DAGGER. That's data set aggregation. So the thing that DAGGER does is it's an iterative algorithm. And it's going to find, it's guaranteed to find a good policy, basically. But what it's going to do is say, if I just collect one demonstration, then when I'm executing my supervised learning, the policy that I learned, then at some point I'm going to get to some state where I have to generalize that I haven't seen before. And with some probability, I'm going to get it wrong. So that's, in this picture, the idea is that if I get just a little bit off of the trajectory of my learned policy, then bad things could happen. So what DAGGER does, in this case, is it says, I'm going to go and follow a policy. So I'm going to follow my policy and get a data set that labels the actions that the expert would take. So the idea is I have this trajectory, I'm following my policy, my guess at a policy, and then at some point I go off the rails, but that's okay. So I just have this set of states, and I have my expert label those states. So it's exactly the places where I get into trouble, which is where I get more data. Yeah?
Is it realistic to expect an expert to label all the states?
Why might it not be? Yeah. So the question was, is it realistic for us to expect a person to label all of this data? And that's a great question. One of the things that you need to think about when you're doing these human-in-the-loop studies is how much can I realistically expect the human to do? So one answer is it depends how much you're paying them. You pay them enough and they will sit there and label every action for you. Another good pointer is if you're employing an undergraduate student, they're more likely to please, especially if you're paying them. But that's a good question because it could be that the person can't act fast enough. So in Dagger, what happens is you collect these states and then you say, okay, now we're going to stop playing the game and go back and label all of the states. In practice, what a lot of algorithms do is say, I have already trained a policy, and I can use that policy to serve as my expert. So we'll see a few papers where we do that. So just for practicality's sake, they just have another policy giving all of the examples. So I get this extra data. I aggregate my data sets, and then I train a classifier, so I get a new estimate of my policy based on this new data set. Now, the one interesting thing I skipped is there's this optional line where we can trade off following my estimate of the policy versus just following what the expert would do. So basically saying on each step, hey, what should I do now? Hey, what should I do now? So in this way, if you have access to the expert in that way, or another way of saying it is if you can ask the person to just play the game, that's a way to get more data directly from the policy. So what happens is typically beta starts at 1, and for the first episode, you get all of your data from the expert, because before the first episode, you really have no idea what to do. And then over time, you decay that, so more and more of your weight of the policy or the action selection goes into this policy that you're learning.
Sir, I was wondering, do we have control on the way that the data is sampled? Or is it more like you're just running this game and you just watch the...
Yeah, so it's more your transitions are controlled by the game. So there are methods where you can like teleport somewhere interesting to ask for more information, but Dagger assumes you're just iteratively playing the game. And that question of if I could teleport anywhere in this state space, where would be the most useful is pretty interesting. Particularly since you could potentially teleport to places that you never actually see in practice. So maybe you're learning a whole lot about this area of the state space that you never actually get to. Yeah?
Do they get smart about updating beta?
Do they get smart about it?
I mean, there's no update of beta here.
Yeah, so they decay beta, just using an exponential decay.
But you could make it reactive, right?
Could, potentially. Why would that be better?
Well, if you're doing well, then you should go down faster.
Yeah. Yeah, so they could do something more clever with beta, more dependent on the performance. Yeah.
Is this like a form of evaluating your demonstrations also? Like saying, can I do better than what the demonstration has given me?
Right. So this is a form of behavior cloning where you're limited by the human's performance. You can't do better. You can generalize. So I should be careful about this. If the person makes a mistake, so if your expert trainer makes a mistake, you still may be able to generalize away from that. But in general, you assume what the person is doing is optimal, and there's no reward in this environment for you to maximize. All you're trying to do is mimic the person. Awesome. Yes?
Is there a way not to go through D every time that you're like updating this file?
A way not to go through D.
The entire data set again and again, right?
Right.
Even though you're having just one new data set.
Yeah, so you could think of doing something more online and incremental. That's not what they chose to do. All right, so if you want to mimic a person, or sorry, mimic a demonstrator, this is one of the algorithms I'd recommend, and probably the place I'd recommend you start, because it's a nice paper. A lot of other papers build on top of it. And here's an example of what was learned. Maybe. On the right, you could see a graph where they're looking at the average number of falls per lap. So typically, that's not going to play. Typically, with behavior cloning, you look at something like how closely did my policy match the humans or match the demonstrators. Another thing you could do is come up with a domain-specific quality that you want to maximize or minimize. So they show here that surprisingly, their method works better than the other methods they considered. All right, so that was if we want to mimic someone or something. Another question is, what happens if we do have a reward signal? How could we combine a demonstration with reinforcement learning? One method is the HAT method, human agent transfer. As an aside, so as you're writing papers, try to come up with cool acronyms. It's so much easier if you talk about the DAGGER algorithm. I mean, that's so cool. HAT isn't quite as cool, but we tried. So we have the HAT algorithm where the first step is someone sits down and demonstrates. So we get a bunch of state action pairs from them. So we get this trajectory, and then we say, oh, hey, this is just data. So we can take this data and just do, like we can do behavior cloning. We can take any supervised learning algorithm and learn a mapping from states to actions. And then now I've got this representation, this policy, my estimate of what the demonstrator is doing, and now I can do something with it. So one of the things you could do is, traditionally in reinforcement learning, we've got explore or exploit. Now we've got this extra option, the execute. So you could say, with some probability, I'm going to just execute the action that I think the demonstrator would have done. And then over time, you could take the probability of doing that execute and turn it down. So you start off just doing behavior cloning. You start off just trying to mimic the human, and then over time, you allow the agent to exploit the Q value that it's learning and explore. Right. In this paper, when was this? From 2011, we looked at a few different ways of combining the action, combining the demonstration with the learned Q values. This one seemed to be the best way. There are other methods that you could think of. So for instance, you could say, I've got this learned policy, estimate of what the demonstrator would do, and I will just increase the likelihood of taking an action that it suggests. So I could bias my action selection towards that policy. You could think of a few different ways of sticking these two pieces of information, the learned policy from the demonstrator, and then your current estimate of Q values, coming up with ways of combining those. Yes?
Do you also take care if you are in a position or in a state that was not in the demonstration so that you cannot really use it? Do you take care of that?
So why can't you use it?
I mean, if you are in a situation where you didn't have the training data from the demonstration, then you don't know what to do next, so you have to switch to your policy level, right?
Exactly. So it's like I paid you to ask that question, because that's the next thing I want to talk about. So, So before I'll come back to that in just a sec. So typical learning curves, x-axis is time in hours, y-axis is performance, and you can see that our method in orange does a little bit better. The important thing here is that we were using just 3 minutes of person time to save hours of simulation time. So the main take-home is if you have a person who can give you demonstrations, it makes sense to leverage them if you care about the total training time. And this has been shown repeatedly in things like Atari, and here we're showing it in the keep away domain. But if you have a person that can provide some bias, great, use it. And if you use a method like HAT, you're not limited by the person's performance. So that's the important thing, because we know that humans are slow, squishy, and suboptimal. So we want to leverage them, we want to use them, and then discard them, or at least their policies. Okay, so then coming back to the question, if I've got this state space, and the person demonstrated a bunch down in one corner of the state space, and then I'm now operating in this other corner. With the HAT algorithm, I could go and ask what would the demonstrator have done over in this part of the state space, and it's really just a guess. There's also cases where you're using the supervised learning algorithm, and maybe it's in the area where the human demonstrated, but because of this supervised learning method, it's confused, and it doesn't have a good estimate of what the human would do. Yeah?
Sorry, in the previous slide you had 3D. I think that was referring to 3 different strategies of exploring, using the experience policy, and exploitation. How are you, like, how the transition between these strategies is happening? Like, is this something, a parameter that is being learned, or is this something that is being?
Yeah, so the question is how do I balance these 3 different strategies? The execute, explore, and exploit. So what we did is we were using epsilon greedy for the exploration. So with some probability, I'm going to explore. And then similarly, we had another parameter that told us how often we were going to execute. So with some probability, we would execute. And at the beginning, that parameter's high, and then it's just decayed over time.
And that is fixed throughout through the learning process. Like, it's not the epsilon greedy.
Right, so with
Parameters are fixed throughout, like during the learning process.
So with epsilon greedy, you typically decay that over time. So you become less explorative. So similarly, we decayed the probability that you're going to execute the transferred policy. So initially, I'm just trying to mimic the demonstrator, and then over time, I rely on my own information. Yeah?
Have you seen such cases that human, like the expert's action is leading to negative transfer?
Good question. So in theory, it's possible. In practice, we don't really see that. So in this domain, the idea is you maintain possession of the ball, right? So the 3 keepers try to maintain possession of the ball from the 2 takers. If you had the human demonstrate a policy where they try to lose the ball as fast as possible, so that you tell them to demonstrate the game of giveaway, then you will get negative transfer. But in general, if we tell the humans to perform the right task, they're usually so much better than random that it gives you this policy, that it gives you this benefit.
Because I'm thinking maybe the policies that the DLRL agent is coming with can be very different from that the expert's policy.
Right, so if there was a huge difference between the type of policies that an agent learned and the type of policies a human demonstrated, then there could be some problems. My guess, though, is that still demonstrating something reasonable would help you learn a lot faster, even if at the asymptote you come up with a very different policy. So, yes?
My question is related to suppose if you have
I'm sorry, more than one? Yes. Great. So the question is, what happens when you have more than one demonstrator? And this gets a little bit into the crowdsourcing literature. So if you have one demonstrator that tells you, if I'm coming up to an obstacle, I have one demonstrator tells me I should go left, one demonstrator tells me I should go right, so what do? I average them. So that's probably not the right way to do it. Another question is, what if I have one demonstrator that's really good at this part of the state space, so really good at doing speed runs in Mario, and I have another demonstrator that's really good at killing Bowser? Then how do I figure out which demonstrator to listen to when? Or in the even simpler case where I've got one good demonstrator and one bad demonstrator, can I learn that? So the quick answer is, if I just take all of the demonstrations and throw them together, then something reasonable might happen. So in the case of this method, the chat method, remember, come up with good acronyms. In the chat method, we have this confidence. So if I have one person telling me to go left and one person telling me to go right, then at that area, my classifier will be confused. So what do we do with this confusion? We say, oh, I only execute if my confidence is above some threshold. So we're doing the same thing that we did before, but only when the agent is pretty sure it knows what the demonstrator intended. So if I'm in some part of the state space that was never demonstrated, or if I'm in some part of the state space where I'm getting conflicting information, then I don't listen to the demonstration, I just listen to my own knowledge. But in coming back to the question, what do you do with multiple demonstrators? That's a pretty open area right now. Figuring out how to best combine them is pretty interesting. Another place where this comes up is in real-time demonstrations or real-time corrections. So there's been some work that's showing if you've got one person that's sitting there waiting to hit the e-stop. So the robot's running around, and you've got one person that's sitting there ready to hit the emergency stop when something that's bad is about to happen. Then they have some type of reaction time. But if you have 10 people sitting there, then the first one, in general, is going to respond faster than the average. So there's some cases where having multiple people watching your robot, you can be better off. But we'll talk a little bit more about this in the future directions section. So with this chat method, we had 3 different ways of measuring confidence. But basically, you can take any supervised learning method that has confidence built in. So it can tell you, for this state, here's the action I would take, and here's how sure I am. Then, using this confidence, you can get significantly better results. Yes?
If you are using neural networks, they are actually very bad at giving you the right confidence of how sure they are about something. Did you see any problem doing that?
So the question is, sometimes when you're doing the supervised learning, the confidence that gets spit out could be really not accurate. Yeah. So that's definitely true. But in the case of what we found in practice was, as long as you set this threshold reasonably, you don't really get into trouble. Because again, if I only look at places where I'm most sure of the demonstration, then so I'm looking at these really good examples, then that still helps me learn faster. Okay, so we looked at behavior cloning with Dagger, and then we said, let's change our action selection. So we've got this execute thing. So we could change our action selection based on the policy that we learned from the demonstrator. Another thing we could think of doing is saying, I want to change my reward function. Wait, what? So I don't think, has anyone talked about shaping yet in the summer school? I don't think so. Okay. So reward shaping is a common technique. So let's say you're in a maze and you get a +1 when you reach the goal and a 0 everywhere else. That's going to take you a while to learn. But if you, as the designer of the MDP, said, oh, let me give you some breadcrumbs. I'm going to change the reward function so that you get a +0.1 every time you move in the direction of the goal. Then you can kind of follow these breadcrumbs to the goal and make it easier. So if you had a real-world reinforcement learning agent and you cared about it learning as fast as possible, you probably would change the reward function to make it as easy as possible for the agent to learn. Of course, that can get you into trouble. Why might that be? So, and therefore, right, so I kind of heard you. So you're saying that you get different values for the states because of the different rewards. And in the extreme case, in some cases, this could lead to different value function, which means a different optimal policy. So for instance, if my goal was to get to the podium, and I get a +1 when I reach the podium, but I guess I get a +0.1 every time I move towards the podium, then I'm going to learn to get really close and miss it. So then I'm getting 0. Now I'm getting +0.1, +0.1, +0.1, +0.1, and then I'm getting 0. So I could learn this looping behavior, because I don't want to get to the +1 where the episode ends. I just want to keep getting that shaping reward. So the researchers found this. When you have a real-world MDP, and you have to specify the MDP, specifying the reward is one of the tricky parts, trying to figure out exactly what to maximize. So one thing you can do is, if you have a potential-based shaping reward, you're guaranteed not to change the optimal policy. So in other words, if I got +0.1, +0.1, +0.1 going closer to it, as long as I get -0.1, -0.1 when I'm going away, then I won't change the optimal policy. So this is the idea of reward shaping. And this is actually a way of injecting knowledge from a human if your human is mathematically savvy. So if your human can write down a potential-based reward shaping function, then you can go ahead and learn faster using that. And you're guaranteed not to change the policy. Of course, most humans aren't able to write this down. But we've got this IRL method, this inverse reinforcement learning method. So one thing you could do is say, I'm going to look at the demonstrations that someone gave me and try to figure out what reward they're trying to maximize. And then I could use that reward function, as a shaping reward. And assuming it's potential-based, so if it's just based on states, then it's a potential-based shaping reward, and I cannot change the optimal policy. So what we were doing with Hat and Chat is we were changing the action selection method. Another thing you could do is you actually change the MDP. So instead of learning the reward R, you will learn R plus this shaping reward. And as you might expect, giving this extra information to the agent lets it learn faster. So that's another thing you might do. You might provide a potential-based shaping reward, and you can learn that from a human, because most of us can't just write that down. But you can have them demonstrate and learn the reward from that demonstration. So I'll say in retrospect, this seems kind of obvious. And it was kind of surprising that other people hadn't done this before. So yes, there's a question. So how does the generalization performance change? So with this shaping reward, or with this reward you're learning, you're trying to learn a reward function that generalizes to the entire state space. So if you have parts of the state space where you didn't get any demonstrations, that reward function might not be very good there. How well it generalizes to those areas, I'm not sure, but that's a really good question we didn't think of. One thing I should mention, so I'm showing a few different ways of combining learning from demonstration with reinforcement learning. One of the frustrating things about this, the field right now, is we don't have a good sense of where one method will outperform another. So right now, we're very much in the era of, look, my algorithm works. And hey, I found a place where my algorithm works better, so I should get a paper. But really, we'd like to know why one algorithm works better than another and where one algorithm will work better. So that's one of the important open questions. Yeah?
So the previous method, when they were trying to estimate the policy from the human, there was this epsilon gradient or exploration idea that was trying to maybe correct some of the human's mistakes sometimes. But if we propagate the behavior in the reward function, then the agent will also learn from the reward. And is there a way that we can correct those mistakes, humans' mistakes?
Great. So in the previous method, we could explore and exploit. We learned to correct problems with a human. In this case, we've got this reward function, and it's always hanging around. We're not learning to correct this reward function. But because it's potential-based, I'm guaranteed to not have changed the optimal policy. So so in the worst case, I could learn a reward which actually slows me down. The reward somehow is kind of duplicitous, and it leads me down the wrong path. But the optimal policy for this changed MDP will still be the optimal policy if I don't have the shaping reward. So I'm guaranteed, at least in the limit, to not change the asymptotic performance. Yeah?
What if the potential is based on state and action? Can you still guarantee?
Yes. So the question is, what if the shaping was based on state and action? And one of the methods, I'm just going to mention this briefly, from 2015 by Anna, who's going to be giving a talk tomorrow, is a way of taking an arbitrary reward function and turning it into a potential-based reward function. So in this case, we can actually do something similar, where we collect a demonstration and then we learn a shaping reward over states and actions. And there are guarantees if you do things the right way, I'll put it that way, then you can get guarantees that you don't change the optimal policy. I'm not going to go into details on this, but it's just another way of taking the shaping function, and instead of over states, you could look at shaping over state action pairs. And in some cases, that can give you better performance. Okay, so with demonstration, learning from demonstration, we can learn to mimic a human. This is done a lot in robotics. Ideally, we want to look at methods where, well, from my perspective as a reinforcement learning person, I'm saying I've got this environmental reward, I better be using it to learn to outperform the demonstrations. And we looked at how we could change the action selection, how we could add a shaping reward. There are other ways we could try to speed things up. But there's a few open questions. Some of them we already touched on. So for instance, the methods I showed today were all providing demonstrations at the beginning. Whereas with Dagger iteratively asks for more data. So you could think of, can the methods go out and say, hey human, give me a demonstration here? Or can the human watching hit a button and say, stop, you should use action 2 instead of action 3. Also touched on multiple demonstrators. There's the question of combining multiple types of advice. So if I have demonstrations and some natural language advice, like stay away from the cliff, how could that be useful? Or in the next section, we'll talk about getting feedback from the person. So saying good robot, bad robot, how could that be combined with a demonstration? And finally, there's the question of estimating the quality of demonstrations. So if I have someone who's playing a video game for me to help speed up the learning, at some point they're going to make a mistake. And maybe they make a mistake really early in the level. Is there a way that I could take that demonstration and realize it's not as useful and downweight it? Or maybe I only want to downweight the states and actions right near where the agent died. We don't know. My intuition is that there's ways to do this, but it's still kind of an open question. Okay, so this was the setting where we've got a person that can help us out by playing the game, and we've got a real MDP. Another question you could ask is, how could I learn from human feedback? So does anyone recognize this picture? Any guesses as what this is? Black and white, think psychology. Pavlov's good guess. So the game of guess what the professor was thinking was B.F. Skinner. So Skinnerian shaping. So in this case, Skinner was showing, I think for Life magazine, how he could teach a dog to jump up on a wall. So the idea is you give the dog a reward, a treat, and then as it starts doing what you want it to, you up the criterion. So initially, dog just gets a treat for coming near the wall, and then the dog needs to face the wall. Then the dog needs to put its paws on the wall in order to get a reward. So there's lots of people have studied how to train animals in this type of giving rewards and punishment scenario. So if we can do it with animals, we've got seeing eye dogs, we have bomb detection dogs. I saw a clip where a Humane Society taught a dog to control the steering wheel of a car. Don't ask me why. But dogs can do all these cool things, so why not build agents that could learn the way dogs can? Well, we're in a RL Summer School, so the answer is I don't need a human. I can just learn from my reward signal. But when you bring a robot home, where is that reward signal coming from? Unless the MDP was pre-programmed, it's going to be difficult for that robot to get reward unless it's coming from a person. So let's think about a little where this reward could come from and how you might use it. One of the first pieces of work in this area was Sophies Kitchen. So if you're like me and you immediately Google for Sophies Kitchen, you get a bunch of advertisements for restaurants. So as most things in this, if you Google for Sophies Kitchen reinforcement learning, then you'll find the right thing. So the idea of this paradigm was just that the human trader provides a +1 or -1. So instead of an environmental reward, we just have a reward from a human. So while I'm learning, I'm going to take an action that's weighted by my Q values, and then I execute, and then I have a small delay. So we can think of humans have some kind of delay between the time they see something and when they react. So we can have some kind of distribution over that. It depends on how confident they are, how comfortable they are with the task, but maybe we could come up with some estimate of that delay. And then I update the Q values based on that reward. And it turns out it doesn't work. At least it doesn't work all that well. Any guesses why it doesn't work all that well? Yeah.
The human is not very good
So it could be that the human's just bad at giving reward.
You need to keep the human constantly.
Yes, so why do you mean constantly?
It has to be there always.
Yeah, so there's this interesting question of, okay, the agent's acting on every time step. What happens when the human doesn't give a reward? So the human hiccups or just isn't fast enough. So does that mean the agent gets a 0? Does that mean we just ignore it? Not really sure. Another problem is if you reward the agent for doing something, and then over time we find that humans provide less and less reward. So now we're getting a non-stationary reward signal. So that could be a problem. Any other guesses for what might go wrong? Yeah?
Maybe the delay would associate the reward with a different action?
Exactly. So if the delay, your guess at the delay of the person is wrong, then now all of a sudden the rewards are getting credited to the wrong action. So you could think of doing some kind of temporal smoothing so that the most recent few actions kind of get rewarded. But that's a little more sophisticated than this original method. Now, one other thing that happened in this research is they found anticipatory guidance rewards. So what does that mean? So in their instructions, they said we're giving feedback on the actions that were taken. So the agent takes an action, you get a reward. The reward was for the action you just took. But what people were doing is assuming that the rewards were future-directed messages or guidance. So things like, oh, you're going in the right direction, or I think you will be going in the right direction. So that, and this is an example of how do humans want to teach. So it's great if we can have algorithms that learn from humans, but if we have to constrain the humans so that they can only provide certain kinds of guidance, maybe that won't be as effective. So what they did is they changed their method so that there was an explicit guidance message. So what they could say is the humans could provide reward for actions that were taken, and now they could also say, hey, check out this frying pan. So if the user says, hey, check out this frying pan, then let's try to do some random action with that object that was just pointed to. Yes?
So here you're talking about random actions, but what about like intrinsic rewards? Like is there a word where you combine both like the intrinsic rewards plus the rewards that you receive from the human trainer?
Okay, good. So what do you mean by intrinsic reward?
Like curiosity so that you can learn from what you haven't seen before.
Right, so there's this other idea. You could think of intrinsic rewards as a type of shaping reward, possibly. So things like if I see something new. So I'm wandering around the room and all of a sudden the light turns on. It's like, oh, I get a little bonus reward because that was intrinsically interesting. So you could think of trying to combine that with either this setting or in the normal reinforcement learning setting. Both of those could be interesting. I don't think anyone has looked at combining intrinsic reward with human-provided rewards. Cool. So this was one of the early methods that worked from human feedback. Another, I would probably say if you're interested in learning from human feedback, I would probably start with the Tamer method. So Tamer is predicated on the idea that humans can provide a reward, and it's not the reward, but it's actually the return. Okay, so let's decompose that a little bit. So we were saying in Sophies Kitchen that there's this anticipatory guidance. Well, if I just let a human give me rewards, I can have that H be a model of the sum of the rewards a human gives me, and as long as I maximize those human rewards, I will do the right thing. And the human's going to provide rewards. The hypothesis is the human will provide rewards not just for the most recent action, but for the direction I'm going. So we can learn to maximize the human's reward, and we could combine this with reinforcement learning. I'll show you how to do that in a second. Let me take a step back. Before we were looking at learning from demonstration, you get a lot of information, a bunch of state action pairs, very dense. Here, we're getting a lot less information because the human's probably not providing us rewards on every time step. So one of the reasons you might like this paradigm is that in some cases, it's much easier to provide evaluative feedback. So the example that Brad Knox uses is, I don't know how to fly a helicopter, but if I'm watching a remote helicopter, I can give negative feedback when it crashes. And I can give positive feedback when that remote helicopter is hovering. So even though I can't joystick the helicopter, I can still provide useful information. So there's a couple of settings where this paradigm is useful. One is where I can't play the video game, I'm just not good enough, but I can still provide feedback. Or maybe there isn't a video game to play. Maybe I just have an agent that's in an environment and it needs to figure out what the heck I want it to do. There's no environmental reward, so I'm going to provide this reward. So in Tamer, we're trying to maximize the human's reward. Now let's see if the video works. Nope. All right. So this is an example of playing Tetris using Tamer. And on the left-hand side, you get random behavior. And on the right-hand side, you see after training, it actually performs pretty well after just 2 episodes. So one of the nice things about this evaluative feedback from the human is it often is very useful. It's very good at providing you a gradient to climb. But here's some of the ways that we could take Tamer, so learning this reward signal from the human and combine it with reinforcement learning. So first, we could think of reward shaping. So what is my reward? My reward is the environmental reward plus what I think the human's going to give me times some discount. So I could try, basically the agent is getting this little extra reward for doing what it thinks the human would do. Another way of biasing is to change the Q value. So I'm actually going to take, when I'm figuring out how to update my Q value, I'm actually going to take my real Q value and add this to it, what I think the human would reward me for this action. There's also action biasing and control sharing, other methods. But there's a bunch of ways that Knox and Stone looked at combining this human-provided reward with the MDP reward. And again, because they're different things, the MDP reward is just on the time step, what you get for that action, whereas the human reward is generally longer look ahead. So it can be very useful for figuring out what the human wants you to maximize. Okay, so if you've got a human in the loop who can provide feedback, I recommend looking at Tamer. That's one of the good methods, and it's relatively simple. So we haven't covered DLRL yet, but one of the unfortunate things that happens a lot is we take an existing method and say, look, it works in deep learning too. This paper is a little more than that, but look, Tamer works in deep learning too. In this particular case, it's an example of Atari bowling, where they're able to learn in a matter of minutes to outperform an expert human. So here's an example of maybe they're not great at playing the game of bowling, but they can still give evaluative feedback that's useful. Yeah?
On your previous slide, you were saying that they used eligibility traits as reward. Can you elaborate on that?
Maybe. Let me remember. So this was the idea that the human reward might not be assigned to one particular action. Instead, think about an eligibility trace over the actions for human reward. And they follow some kind of shape based on how recent they are. Credit assignment. Yes. Okay. Awesome. So Tamer is cool. I want to briefly touch on one more method. And the difference here is thinking about it from a dog training perspective. So I did some work with Michael Littman and David Roberts. And Dave Roberts is a computer science professor who's also an amateur dog trainer. So go figure. He was, so you can do Skinnerian shaping with all different kinds of animals. And he was so excited when he went to the chicken teaching workshop. So they using shaping, using these methods of giving rewards, they're able to teach chickens to do tricks, right? So if you can get a chicken to run through an obstacle course, how much better can you teach a dog? So thinking about how the dog learns, well, in Tamer, you get a +1 or a -1. That's all the human is giving you. You just have 2 buttons. So there's a couple of questions. First, does it really make sense to assign numeric rewards? So when I say good job, is that really a +1 or is it a +5 or a +4.5? Well, that would be 2. But you get the idea. The other question is, what do you do when there's no feedback? What do you do when the human says nothing? So we assume that there's some desired policy, and we've got a history of the training policy, and we do the normal thing where I've got some model of the training process, and I've got some prior distribution over policies, so I can figure out what the map hypothesis is. So what is the most likely hypothesis? So in order to do this, we need a couple of assumptions. One of them is that the human makes some error. So with some probability, you just hit the wrong button. And we also make an assumption that there's some probability that you give positive feedback when the agent does the right thing, and there's some probability you give negative feedback when the agent does the wrong thing. And these probabilities might be different. So think about dog training. So you've got this puppy. For those of you who don't know, when your puppy does something wrong, you're not supposed to hit it with a newspaper, right? And when it poops inside, don't shove its nose. That's not good. Instead, you're supposed to give positive reinforcement to the puppy. So when it goes poop outside, you give it lots of praise, right? So there's some indication that for some types of training, you want to give positive reinforcement. Whereas if you're teaching a class full of undergrads and you've got a grade, you're not going to go and say, oh, good job, good job, good job. No, it's much more fun to just go big red X. Just mark the places where they messed up. So we hypothesized that people might have different probabilities of giving positive feedback and giving negative feedback depending on the task. So we ran Mechanical Turk studies. How many people have heard of Mechanical Turk? Okay, good. How many people have used it? Very few. Okay. So if you do human studies, you're probably going to wind up using Mechanical Turk because it's such an easy way to collect data. So basically you're paying people, you can pay people to come and do your experiment. In our case, we paid them to come and teach this dog to scare a rat away from the field. So you can see a green flash. That means the person gave a positive reward when the dog correctly scares the rat away. And what we found is the majority of people, well, let me start here. 93 of the participants mostly gave reward when the dog did the right thing and gave punishment when the dog did the wrong thing. So explicitly said bad dog. The majority of people said good dog when the dog did the right thing and said nothing when the dog did the wrong thing. So that means that different people, so in this case, saying nothing, giving no feedback, actually means, hey dog, you messed up. And what this method, this SABLE method does, strategy-aware Bayesian learning, basically looks at the evidence for the task and figures out what's the most likely. So, okay, here's the graph. So for instance, if I look at this bars on the right, how long does it take me to reach some criterion? So to reach some performance. So lower is better. So in our case, if we're able to figure out, are these people using neutral to mean bad dog, then we're able to learn faster. The competition here is doing nothing when there's a neutral, so not updating at all. Just so if I treat good dog as +1, bad dog as -1, I could treat neutral as nothing, doing no update, or I could treat neutral as 0. So both reasonable things to do. In this case, if you can infer what the person is doing, then infer what they mean by no feedback, then you can learn faster. So this is a different way of learning from human feedback, different from the Tamer method. I think it's cool, in part because I was a co-author, go figure, but if you're interested, I would actually recommend Tamer as the place to start. Okay, I'm going to skip this and just show a video real quick, if there's sound. Oh, the video's not working. Then I'll just mention this briefly. The other thing we looked at is the idea of implicit feedback. So you can think about the dog saying, oh, I need help. So I'm confused, give me more feedback. So there could be a little pop-up for that. Instead, what we decided is we would have the speed of the avatar depend on how confident we were in our policy. So if the agent is very confident, it goes quickly and minimizes wall clock time. If the agent is confused, it goes slowly and maximizes the chances that the human will give it extra input. So this is a kind of implicit communication trying to elicit extra feedback from our human. And there's a bunch of research that has to do with how do we best get information out of our human. So you think of how do you teach the teacher? Or how do you shape the teacher so that you get the most useful information? Oops. And my computer froze. That's awesome. Oh, hey. Whoops. Let's see. So I've got 6 minutes left. So I'm going to skip over this. Just a third method I wanted to mention called policy shaping out of Charles Isbell and Andrea Tomas's lab. So policy shaping is another method which has some nice theoretical guarantees, and you can learn from humans. It's a little more complicated than the others, but it shows quite a bit of promise. So, where does that end? Okay. So great. So humans can train agents to do interesting stuff. I focused on virtual agents, but you can also do this with physical agents, so robots. There are cases where you can combine an environmental reward with human feedback. There are some cases where providing this type of human feedback may make more sense than learning from demonstration. So one of the areas where we need to think more about is how humans want to train. We really want to bias our methods towards the easiest thing for the human to do. And that's going to take some psychology. Also, if we understand what the human biases are, we can better leverage them to learn faster. Also, we and others have done work on curriculum learning. So if you've got this difficult task, it probably makes sense to train the agent on something simpler first, and then gradually increase the difficulty. So this is the idea behind the Skinnerian shaping, which I began this section with. You want to start simple and make it harder over time. Cool. So the very last thing I wanted to do is just mention, if you're interested in doing these types of human studies, it's a lot harder than you might think. Part of it, so the first thing is you kind of got to get inside the person's head. So if you've got someone who comes into the lab, why are they helping you? Is it because they're your friend and they're going to give you high quality data? Is it because they're an undergrad and you're giving them 50 cents for their time? On Turk, you often get people who are trying, there are a few people who go through and just try to do the tasks as fast as possible in order to get their 50 cents. So you may want to set up the task so that someone can't just click through as fast as possible. But there's lots of reasons why you might be getting people to do a task for you, and knowing something about their motivations may help you design that task. It turns out that there aren't a lot of malicious people. So there are some people who just want the world to burn, right? So they will go on Mechanical Turk and just give you awful data, but you can often filter them out. So for instance, by what are called gold tasks. So asking questions where you know the answer, or having places where it's obvious what the right thing to do is. If they do the wrong thing, then you know you can throw out their data. There's one cool example, though, where some researchers showed that people were basically truthful. So what they did is they said, on Amazon Mechanical Turk, I want you to roll a die. If you don't have a physical die, here's a different website you can go to and roll a virtual die. So roll the die, tell me what you got, and then I will give you money based on what you just told me. So you get 25 cents plus 25 cents times whatever you rolled. So if you're an economist, you would look at this and say, this is stupid. Everyone's going to say 6. But it turns out, if everyone was honest, we'd get a 3.5. For a single roll, we get 3.9. If we ask them to do this multiple times, we get 3.6. So people are not maximizing their expected payoff. Instead, they're actually telling the truth. So I thought this was pretty exciting, that there's some indication that random people on the internet who are getting paid just a tiny amount of money can give you good data. So there's some payment guidelines. Basically, think about the US minimum wage. There are lots of Mechanical Turk tasks that are less than that. But if you want to get reasonable data, it's better to pay for it. Task design is important. Here we go. Pilot. Whatever task you come up with, you're going to do it wrong the first time. So you need, anytime you're interacting with humans, it's amazing how good humans are at misinterpreting the task. You know, coming up with an error between the chair and the keyboard. And you need to have multiple pilots, so try multiple times to figure out the ways people can misinterpret your results. And lastly, there's the matter of the IRB. So if you are doing human subject tests, you probably have some paperwork to file to make sure you're not causing long-term psychological damage. That's something we like to avoid. All right. So hopefully you found this interesting. Hopefully I motivated why you might want to use a person or how you could use a person. There's not one great resource for this interactive machine learning. So that's a general keyword you could search for, is interactive machine learning. This book, Robot Learning from Human Teachers, is probably the most relevant book. But there's not, as far as I know, there's not a great survey on this area because it's relatively new. So if this is interesting, you're going to have to do a little bit of Googling. So my slides will be posted soon, and I put all the references at the bottom. So hopefully this will give you a kicking off point. But more importantly, hopefully this has given you something to think about, because this area is really wide open. As we get agents that are deployed in the real world, they're going to have to be human aware. They're going to have to learn from human teachers. And I presented a few ways that that could happen, but I'm sure there's many more. So hopefully some of you will go out and find the next best thing, and your graph will be a little bit higher than the existing line, and you'll get a NeurIPS paper. So thank you.
Time for one question.
I'm sorry, can you speak up?
How about keeping another human or another agent in the loop as well as like knowledge distillation kind of thing?
Yeah, so I talked about human in the loop. What about agent in the loop? So in some cases, if you have an agent, you could do something like transfer learning or knowledge distillation because you have access to their brain. It could also be that you don't. So I've got a robot from Samsung that's trying to learn from an LG robot, and there's no API for those two robots. Then maybe I could still use these techniques that assume a human. So having one robot provide feedback or advice. But you're right, if you can get at the brain of an agent, having one agent teach another opens up a whole nother world of possibilities.
So one